Putting this thing on makes me sort of self-conscious given the topic. I can sort of picture this as a tracking device so that Nicholas can see if he can duplicate the pattern of my life. I'm going to start now. Is it okay? Are we ready? I'm going to start now because I've just learned that a lot of people are in a meeting with Sheila Kennedy, and as soon as that gets out, we'll probably get a lot more people in here, and I certainly don't want to interfere with the director's search. So, but I'd like, what do you think I am, a bat? I'd like to let Nicholas get started because, for one thing, I'm dying with curiosity. I met Nicholas, gosh, what is it, a year and a half ago. And there was some kind of, was it an auction or something here, and Marty came up to me and said, it was an open house, right? There's somebody I want you to meet. And here's Marty sort of standing there, and along comes Nicholas. So I'm sort of like overwhelmed by these two people. And Marty says, well, Nicholas is an anthropologist of artificial life. And the minute he said that, I fell in love. I was just blown away. And I think you see it too, the combination, the sort of completely humanist idea of anthropology, and then the purely computational idea of a computer combined in artificial life. It's obviously just too delicious to pass up. So we talked about the possibility he was coming. At that time, the lecture series wasn't even started, but I was planning it and starting to make a list of people that I wanted to invite. And fortunately, Nicholas was able to come here. So I'm going to let him tell about his background. His background is just as fascinating as his profession. He started out as an engineer at UCLA, and then I'll let him describe to you the motivations for the various morphs in his life. But he ended up doing anthropology and archaeology, particularly in the Pacific Northwest, I guess. And then, like any good anthropologist, this was in the 60s too, which, if any of you have been exposed to the intellectual currents of that time, structuralism in anthropology was the go-go theme, and it looked as though all societies could be described in a set of binary oppositions, which of course then could be modeled in a computer or some kind of algorithmic process. And Levi-Strauss, although not the originator of that concept, it really came from structural linguistics, was still the kind of granddaddy of it. I remember I lived in Europe at the time, and if you didn't know who Levi-Strauss was, you were just like, no salon in Paris was open to you, that's for sure. And so it was a very exciting time because it combined ideas of Marxism, and as you know, back in the 60s, the idea that society could take control of its own destiny became the sort of hallmark of an entire generation of which I was part. So I'm now kind of reduced to, or elevated to, depending on how you look at it, trying to change SCI-Arc instead of the whole world. It's a lot harder to do on a local basis, I can guarantee you that. So the issue of theorization came up, and it came up for Nicholas too, and he decided to look into computational methods for building or theorizing a structure for anthropology. And so we're going to see the results of 15 years of work today, which I guess is an ongoing research effort, and if you visit his webpage, you'll be delighted. I mean, it's really a great place to surf around in. So I'd like to introduce you to Nicholas Gessler, who's at UCLA. Nicholas?
Yes, Okay, the instructions I received were to make it personal and porous, so I'll attempt to do that. What I've put together, there are kind of three this is a multimedia presentation with whatever glitches happen along the way. It's going to start off with a computer-based demonstration with some software demos, then we'll go to some slides, and then at the end I have some videos of somebody else's work, which is quite exceptional. I've always been interested in science since I was a kid. I was born in Peru, grew up among artifacts, grew up in a virtual museum, I mean a real virtual museum, not a virtual museum. So archaeology, science, technology were always sort of in my blood. I went and started at university in engineering, was more interested, well, I got tired of measuring the lengths and diameters of ball bearings and things. Went into anthropology, thinking of going into archaeology. And let me just proceed through this. If you have questions, please feel free to interrupt me at any time. I'm going to try to charge through a lot of this so that you do get an opportunity to see some of these demonstrations, which are quite exceptional. Okay, let's see. How can we explain this bar? I guess we won't. I'm thinking of a good story. We have a refresh rate incompatibility. Anyway, the name of the talk is Computationist Manifesto Towards Artificial Culture. And this is one of my icons, I guess. This is a connection machine Model 2. If you saw Jurassic Park, you saw a connection machine Model 5, big black boxes with red blinking lights. This is an early parallel supercomputer, and it's now in my garage. So I also collect technology. I'm hoping to get a second one that works. And if I forget to mention it later, the video that we'll see at the end was done on this machine. That's also going to explain why it's not going to be, why it's on a video and why I'm not trying to create that simulation for you on a PC. Okay. So when I first heard about SCI-Arc, I thought, oh my gosh, Sci for science and Arc for archaeology. And then I found it was Southern California Institute for Architecture, and I thought, oh, well, that's cool too. Okay. So there's another thing in my collection. So that was the science. This is the archaeology end. I was born in Peru. I can't claim to have done any work at Machu Picchu, but it's a neat place, and it's a connection between archaeology and architecture. The things I want to pursue now, which are not usually pursued in anthropology, are the blending of evolution. This is, of course, Charles Darwin and Wallace, the originators of the idea of natural selection, computation, science and culture, and technology. We just came, just last week, from doing a workshop on computational, what do we call it? Computational social science. Not a very exciting name, but it's the first time that we put on a workshop, and we're hoping this is going to lead into a book. One of the things I'm trying to do, and some of my colleagues are trying to do right now, is to gain some academic recognition for this line of research. One way to do that is to hold conferences. The other way is, of course, to publish books and promote it in various ways. So we just did this workshop just last week. I managed to twist the arms of the American Anthropological Association and get them to invite a session on computational anthropology at their next annual meeting. They decided to change the title. They called it Computing the Future of Culture, New Approaches to Understanding Cultural Dynamics, which is just fine. So what I want to talk about, what's new about the kinds of stuff that we're doing. What's new is that it's a combination of evolution and computation. So we also may have a conference next year at UCLA on the evolution of computation, and you flip that around, the computation of evolution. But just take a quick look at this. The evolution of computation basically starts 50 years ago in 1950, comes up to the present, and by the way, there are Hal's birthday celebrations going on at this very moment in Illinois. That's where my wife is. Arthur Clarke is speaking, and Roger Ebert, various Marvin Minsky, various other people. Hal, you all know who Hal is from Clarke's 2001. Okay. Putting this in sort of an anthropological perspective, we've gone through 2 million years of making artifacts that leverage matter and energy, tools, materials, structures, and features. 35,000 years of making artifacts which leverage information, physical models, representations, and art itself. And only 50 years of making artifacts who think. Computers. And I think this is as big a revolution as any we have had in the last couple of million years. And we're only beginning to see the results of it. As far as the computation of evolution goes, this is doing evolution on computers. That seems to have started around 1970 with, added benefit. I can point and my finger actually comes up on the screen. That's neat because I was doing a similar presentation just 2 days ago and I was wanting to be able to do that.
You improved the mouse.
Yes. Okay. So, wetware. This is really neat. I don't know if any of you are aware of this, but there have been 2 or 3 articles in Science about using RNA and DNA to actually compute mathematical problems. That you set up you set up a mathematical problem, you encode it into DNA and RNA, you evolve it in a test tube to get an optimized molecule, and you decode that molecule to give you the answer to a mathematical problem. That's pretty neat conceptually. Software, things that you can run on your PCs and Macs. Got genetic algorithms, evolutionary programming, evolutionary computation, evolutionary strategies, and something called genetic programming, which is the newest, hottest thing out there. Basically, how many of you have done programming? 1, 2, 3, 4. Okay, well imagine that you can set up inside of, it's hard to do programs, okay? What if you just said, I know what I want the program to do, create for me 1,000 programs at random. I'm just going to test those to see how well they do. So I'm going to establish a fitness function. The computer will generate the programs, run them, evaluate which ones are better, which ones are worse, take the better ones, mix them together, mutate them, populate a new generation of them, and so forth. That's genetic programming, and it's a pretty powerful tool and a very interesting one. The last one is equally interesting. Hardware. At the last Artificial Life Conference, somebody got up and gave a talk about software computation, and he said, gee, wouldn't it be neat if we could make the hardware evolve instead of the software. The next guy who got up to give a talk on just that. So we have these things called field programmable gate arrays, which can be configured by software. They actually then are hard and soft and hardware, and you can basically evolve your own microprocessor if you want. There's somebody working on a large computational project who envisions a computer that runs more or less as follows. You turn the computer on and you say to it, okay, this morning I want you to be 10,000 pentiums. Okay, it configures itself as 10,000 pentiums. You give it a problem, it runs the problem. Or you can say, configure yourself as 10,000 or 6 Motorola's CPUs and a Zilog 80 and some other analog chip. And it'll configure itself that way. So this is pretty neat stuff. Okay, so here's my scary warning, borrowing from Karl Marx. The specter is haunting science. We've discovered our creator, namely natural selection and evolution. We've captured our creator. We've embodied it in our machines, and we're now in the process of dispersing basically evolution in these machines throughout the world. There's something called the modern synthesis in biological evolution. It's a combination of natural selection as proposed by Darwin and Wallace, and a combination of genetics, which was discovered by Mendel, but really wasn't developed until the 20s. And when both of those were brought together, it was called the modern synthesis. So I think we're at a junction which is just as important. I like to call it the postmodern synthesis, since it seems to bother the humanists, and we get into interesting discussions by doing that. But essentially, we're talking about artificial intelligence, which you've all heard of, artificial life, which has basically it's subdivided into three fields: wetware, software, and hardware. The wetware is like creating things in test tubes, software is computer programs, and hardware is robots. Autonomous agents, there was just a conference at the Marina del Rey on that subject, a very exciting conference. Artificial Society, one of my colleagues has come out with a book by that title. And Artificial Cultures, which is the project that I'm working on, and hopefully we'll have a book out by the end of this year. Okay, so what are the concepts in this new way of thinking, paradigm, or whatever you care to call it? Emergence. I don't know how to define it to you. Basically, in artificial life, we talk about generating complex patterns from simple rules. So you have local rules, that is, small parts that get together, they interact, and they produce a general behavior, a global behavior, which is a bigger thing. But that bigger thing is nowhere within the heads of those little agents that produce it. So this is sort of the concept of emergence. I'll show you some examples of that. One neat thing about the concept of emergence, if you listen to Marvin Minsky talk about it, he says, don't listen to people who say, oh look, I found this neat emergence in this computer program. He says, when they talk about emergence, what they're saying is, I'm too stupid to understand what's going on. Okay, that's right, but that's also very important, because what that says to me is that the human brain has not evolved to be able to calculate the consequences of lots of little things happening all at once. So this, to me, it's a phenomenon, it's something that's happening, and I think it's evidence for the counterintuitive nature of this kind of work, and also an argument for doing it. Algorithms, processes, that is an emphasis on process and plans and methods of how things are getting done, rather than algebraic or mathematical models of something. Multi-agency, this is another popular notion, that is, you have a whole bunch of agents all working together to produce some desired outcome. The agents themselves don't know what they're doing, but the outcome, the behavior, the composite behavior of all this activity is interesting. And of course, evolution, and you're probably aware of how natural selection works, by amplification, selection, and recombination, or reproduction, fitness evaluation, sex, recombination, mutation, those sorts of things. In 1971, Jay Forrester made an interesting statement in an article called The Counterintuitive Behavior of Social Systems. Essentially, he said, well, to quote him, he said, "It's my basic theme that the human mind is not adapted to interpreting how social systems behave. In the long history of evolution, it's not been necessary for man to understand these systems until very recent historical times. Evolutionary processes have not given us the mental skill needed to properly interpret the dynamic behavior of the systems that we're now a part." So it's another manifesto for computer simulation. In the same year, 1971, does anyone know Stanisław Lem? He's a science fiction writer, although I hesitate to call him that. I think I would prefer to call him an anticipatory philosopher of science, because he's right on so many times. He wrote an interesting story back then called Non Serviam, a short story in which he describes a field which you'll see describes the kind of work that I'm doing and a few other colleagues are doing. Personetics. At present, a world for personoid inhabitants can be prepared in a matter of a couple of hours. This is the time it takes to feed into the machine one of the full-fledged programs. There, and he listed several of them. A specific type of personoid activity serves as a triggering mechanism, setting in motion a production process that will gradually augment and define itself. In other words, the world surrounding these beings takes on an unequivocalness only in accordance with their own behavior. As hundreds of experiments have shown, groups numbering from 4 to 7 personoids are optimal, at least, for the development of speech and typical exploratory activity, and also for culturalization. On the other hand, phenomena corresponding to social processes on a larger scale require larger groups. At present, it's possible to accommodate up to 1,000 personoids, roughly speaking, in a computer universum of fair capacity. Studies of this type belong to sociodynamics. There have arisen many different philosophies, ontogenies and epistemologies. Now he's talking about philosophies in the heads of the personoids inside the computers. Interesting idea, and actually somebody's done something similar to that. And then he ends by quoting the author of this work, who claims, I can enlarge their world or reduce it, speed it up or slow it down, alter the mode and means of their perception, the personoid's perception. I can liquidate them, divide them, multiply them, transform the very ontological foundation of their existence. I am thus omnipotent with respect to them. I'm going to skip a couple of slides. These are some quotes by some recent anthropologists who are trying to invoke cybernetics to understand anthropology, trying to invoke cognitive science. I'll just skip to the foundations of anthropology that I use. Basically, my work comes out of the theoretical work done by Marvin Harris, a strategy which he called cultural materialism, and Louis Binford, an archaeologist, a strategy which he called processual archaeology. They both stress process and matter and energy relations. And I think these are particularly applicable to general specializations in anthropology, which are the specializations I'm working in, developing theories of culture change, of cultural and biological evolution, and of course, included in all that are science, technology, and culture. Okay, what's wrong with present notions of culture? How do we feel that we can break through some of the impasses that have been around in anthropology for a few hundred years? Well, culture is often seen as a norm, or taken as a norm. Even though we recognize that when we're teaching, it's because we have to teach using, here's my argument against discourse and language. We have to teach using language, teach using discursive language. It's very easy to get into the habit of talking about norms, and it's very difficult to talk about complexity. So there are a number of abstractions, and I propose some solutions to those. One is this notion of spatial homogeneity, that is, anthropologists tend to talk about culture as average, okay, the average of everybody. Well, nobody's average. It's the interaction of different people that make society work. There's a notion that individuals behave consistently. Once you figure out what the culture is of a certain society, what's in the head of those individuals, this is generally applied consistently by those individuals. If you look at Minsky's work on the society of mind, you'll find some alternative ways of looking at the mind. You mentioned Levi-Strauss at the beginning and structuralism and how this emerged from linguists' idea of thought. There are other models of mind around which we would like to invoke in this kind of research. Referential accuracy, that is, we assume that people in cultures generally have access to the information that's around them. Well, there's information and misinformation, and people don't have global knowledge. We talk about shared beliefs. To me, this is a very strange one, because it seems to me it's the differences that, sure, we have certain shared structures in our heads, but it's the differences that make things happen. You're all here in this institution to learn and exchange ideas, and if you have to exchange ideas, that means that there's different stuff in your head. So it's the differences that make for interesting things. Cultural anthropology generally tries to identify typical individuals instead of looking for a co-adaptational population of individuals that exchange goods and cooperate with one another. And as I mentioned, there's a tendency to talk about global knowledge instead of local knowledge. And to talk about anthropology and culture and frame it in terms of lectures, discourses, books, and monographs instead of trying to model it in another way. And I think since you folks, the end product of your work is to build buildings, the end product of a lot of anthropological work is to write dissertations or to take up the role of an activist for a certain society. The point of artificial culture research is to, as an end product, to model that society, build a computer model of it, and try it out. So it's a public, what is artificial culture? I won't read this to you, but basically it's creating inside the computer a population of individuals. Each individual has cognizers, that is, things that process information. It has sensors that it can derive information from the local world, and it has actuators or motor processes that lead to behaviors. Now, you take these individuals, you throw them into a computer on top of an environment that you had already put into the computer. Now, that environment consists of a space and some sort of a physics and space and time relationship. And essentially, you turn them loose and see what they do. The last 4 slides were a discursive explanation of that, trying to put it in a nutshell, but it fell into 4 nutshells. Okay. What I'm going to show you is just one of the demonstrations, just a very simple demonstration of foragers. If we look at this screen, this is a bird's eye view of a 100 by 100 area into which food has been thrown at random. Now, there can be 1 unit of food or 150 units of food thrown into any of those cells, any of those 10,000 cells. The more food there is in a cell, the warmer the color on this visualization. So red and white means there's a lot of food in that cell. If it's blue or black, that means there's not much food left. So what I've done in this very simple demo is to throw 10 agents into that system with a very simple rule that says, look around you to the 8 neighboring cells, see where there's the most food, go there, and eat your ration for that turn. That's the simple rule. Now, if you look at papers on optimal foraging strategy and so forth, there tends to be a mathematical relationship between the amount of food available in an area and, well, the appetite of the individuals. They don't usually control for the distribution of food in space or the number of individuals. So what this little demo does is to try to see how picture will change if you introduce the notion that the food isn't isn't evenly distributed, and introduce individuals with different appetites. So this is a beginning world. If I throw down food at random, okay, so they're random colored dots. I think you can follow that. And we let these guys eat until they run out of food. That is, as soon as an individual has eaten and there's no food in the surrounding 9 cells, 8 cells, the individual dies and stops. When everyone is dead, we count up how much food remains. So this is the beginning amount of food, the ending amount of food. And then we, having done that, we change the ration. So if they're going to eat 1 food unit per turn, this is an axis of from 0 to 100 food units. And this is the efficiency. So if they eat 1 food unit, they're generally about 90% efficient. If they eat 10 food units, about 95%. And then the larger their appetites, the less efficient they become as a rule. Each dot on this chart here represents 1 run of this simulation. So this chart is a composite of 10,000 runs. And I don't think that you could have predicted the shape of this curve by any of the standard methods used in foraging type algebras or formal logics. Okay, this may not be terribly unexpected. I think people have asked what the curve would look like, would say, oh, well, it's probably some kind of a straight line, or maybe a simple curve relationship. And for a random food distribution, okay, well, you get a lot more variation the hungrier these individuals are. But it's not a straight line, but it's not that complex either. But let's change the food distribution. If it's a uniform food distribution, they basically get almost all the food. By the way, these little green dots are the individuals in the positions where they are resting in peace. They've eaten, they're dead. Here you get almost 100% efficiency, but there are different thresholds where the distribution of efficiencies breaks qualitatively. An inclined food distribution, so there's no food in this corner, and this is coming up towards you, so there's a lot of food in this corner. Very interesting thing begins to happen here. When you do 10,000 runs and increase the appetite or the rations of the individuals, you'll find a couple of bifurcations in this distribution of efficiencies per run. Now the shape of these isn't particularly important to you, I don't think. It may be to me. But what I want to point out is this is the kind of result that you could not get unless you ran a computer simulation. Here's a cone, like Mount Fuji, a lot of food in the center, not much towards the periphery. You'll notice that there are several approaches, there are several curves in this composite of 10,000 runs. And that I would call an emergent phenomenon. What is happening here is these critters, you can see the little green dots, they've managed to isolate themselves in rings. They do a kind of a mowing structure to eat this food, and they kind of destroy the gradient that tells them where there still is food further away. So they end up on little islands that they've created. If we take that peak distribution and turn it upside down, so there's no food in the center, a lot around the edges, you can see how there's a cluster of dead individuals here, another cluster here, another cluster there, which corresponds to these different approaches into this efficiency curve. All of this stuff is nothing you could not predict from standard methods. If you put in a lot of peaks, you get a more complicated pattern. Turn it upside down, make it a lot of valleys, it becomes even more complex. Okay, so what does this have to do with anything? I think somebody was asking me about concepts and so forth. To me, this kind of work basically is putting forward, it's questioning present theories of knowledge. It's certainly questioning present philosophy and epistemology. There is beginning to appear a literature on natural computation, which basically means the evolution of cognition, evolutionary epistemology, genetic epistemology, and nothing yet that's been called computational epistemology, but there's certainly people out there who are talking it, even though they don't call it that. So I think there's a very exciting future for this kind of stuff. And I'm just about to finish with this and then go into some prettier things. Less talk, more action. It occurred to me that there could possibly be some very interesting things you can do with this kind of work in architecture. One being actually evolving architectures, evolving designs or evolving structures. Second one being to take a space that you've designed, or say, me as an archaeologist, I have a plan of an ancient city, take that space, put it in a computer, throw a bunch of artificial agents in it, give them certain cognizers, and let them loose. See what they do. If this is supposed to be a structure that is to support, if it's a plan of a city which supports trade, turn these agents into traders and see how that spatial arrangement of that city really does support it or not support it. So you could throw agents into plans. A little more concretely, there's been a lot of talk about intelligent materials. Beams, for instance, that talk back to a computer and actually, let's say you've got a beam composed of a whole bunch of agent subparts. Those that are beginning to pick up more stress actually can then transform themselves into resisting that stress. I think there has been some work done on that. Evolving materials, self-assembling structures. The Japanese have been very interested in this, bridges that assemble themselves. When we were setting this stuff up here, I was thinking, my gosh, you know, it would really be nice, these stupid machines, if they were smart enough so that you could throw them all in a room and say, okay, connect yourselves together. Let them assemble themselves. This work is actually being done, again, mostly in Japan. And ubiquitous computing, I think Park Xerox is working on that. Basically embedding computers and microprocessors in the chairs, in the doors, in the urinals is actually where I saw them. So that in the toilets, when you walk away from it, it flushes itself. Those are pretty dumb computers. But I think there are more productive things that can be done, which perhaps some of you will be doing. Okay. I wanted to show you just a couple of quick demos on the computer and then run through some slides quickly and then show you two videos that are really exceptional. The point in going in this order is to hopefully be able to explain to you what makes these programs work in a way that you begin to understand some of these concepts that I've been talking to you about. Do you know have any of you played with cellular automata? Pardon? Conway's Game of Life? How many of you have never heard of it? Never heard of it. Oh, good. At least 3 people. Okay. What I'm going to do here is import Conway's Pardon?
This movie Mars actually emerged.
Right, because we were too dumb to figure out a way to stop it. But yeah, it's an emergence. Okay. Oh, look at this. Neat. Okay. I guess you can't see that. Let me try to... I was looking last night trying to find trying to get this world to do exactly this, it wouldn't do it. And so this has emerged spontaneously. This is a world that is a grid world. You can see the size. Okay, you can see the size of the dots. Maybe. Whoops. Can't do both, can I? No. I'll leave it like this. Pardon? It's a grid of cells, individual cells. And the world consists of a number of time steps. And the way it works is more or less as follows. At each time step, each cell can be one of 4 different colors. There is I hope I can do this without killing these creatures, because I'll never find this again. Okay, and the rules, well, this says that if you're gray, and you look at your 8 neighbors, and you count how many neighbors you have. And let's say you have no neighbors. If you're gray, you'll turn gray in the next move. If you're blue, you'll turn gray. In fact, you'll turn gray in the next move if you don't have any neighbors. Okay. If you have one neighbor, no matter what color you are, you'll still turn gray. If you have 2 neighbors, you'll stay the same color that you are. Can you all follow that? I guess that shows. If you have 3 neighbors, you'll change color according to this little diagram. If you're gray, you'll go blue. If you're blue, you'll go red. If you're red, you'll go green. If you're green, you'll stay green. If you have 4 neighbors, you'll go gray again. 5 neighbors, you go gray, and so forth. So there's nothing, that's a rule that's applied to each cell in this world. There is no rule that says if you're a green square that's 2 by 2, you'll stay there. There's no rule. It's an emergent property, a consequence of these other rules. There's no rule that says if you have such and such a configuration, you're going to bounce back and forth, and you're going to give off these little particles running up to the top right of the screen. So these are all emergent properties of a cellular automata universe. And philosophically, I think this is important too, because it brings up the question is, wouldn't you call this an object? Isn't this something? Is this an object that's moving there? In the rule structure, there is no object like that. So it brings to question a lot of things philosophically about what objects are, what patterns of behavior are, what is a flock, what is a group. In fact, there's a physicist. Does anyone know the work of Ed Fredkin? He's a millionaire, and he does a lot of lecturing at MIT, and basically he has modeled basically all the phenomena of physics, except I think for some aspects of quantum theory, using cellular automata. So this is an example of really dumb stuff, really stupid stuff that is beginning to produce maybe not terribly interesting, but certainly some surprising results. I'm going to kill that, but you notice if you build 3 squares like that, you get a little, I don't know if you can see that, you can't. My apologies. But if you can create different structures, they will inevitably all follow higher level patterns. Okay. If I create 3 rows, link 3 dots together, make them blue, they'll turn into a cross that alternates between vertical and horizontal. The video that I will show you, well, let me say, with cellular automata, I don't have time to show you all of this, but you can actually replicate a whole computer and electronic circuitry in cellular automata. You can replicate binary counters, you can build logic circuits, all based on cellular individual stupid rules.
Okay.
I'll just show you, I showed you some diagrams of the results of a simple foraging exercise. This is, whoops, can't quite see here. I'm going to tell, this is an artificial culture forager experiment. I'm going to tell the computer that these critters are going to eat 10 food units every time, and I'll tell them to tell the computer to distribute the food in peaks. Now this is not displaying the colors too well, but when the gray bar comes over, you get a different relationship. Here's some other emergent properties, these things that look like moire interference patterns. I'll try to, let's see, where are we going? Reset. Okay, this is the cone, the conical distribution. Probably can't see it too clearly, but when this begins, all of the agents rush up to the center of the food distribution, and they mow their way down the edge. And you can see that they tend to isolate themselves in concentric rings. So these are other emergent properties. So I've left this up here for about 20 seconds, and it's gone through 3 runs. Those composite diagrams that I showed you are the results of 10,000 runs, which takes about 2 hours. I'm going to quit this demo and show you something fun. There is already commercial software that makes use of artificial life. This little product is not available in the US yet. It's called Creatures. What you get when you purchase this product is the software and a little disk which contains 6 eggs. You actually have to now, can you see this little creature? Towards the center here, it's called a norm. You actually pull the eggs into the world of this norm, you hatch them in an incubator, and then these creatures are somewhat intelligent. If I wave my hand in front of its face, I can catch its attention. I can teach it I can teach it what foods to eat, what to do, what not to do. I can tickle it. That's the reward. If it does something bad, I can slap it on the rear. It's not politically correct. Maybe that's why it's not distributed in the US. I can pick up this ball, and if I can interest it, it'll take the ball from me. Now this creature actually does have a neural net brain, and the idea of this game is to breed a number of these. When they reach maturity, they begin to take sexual interest in one another. They have kids. And you can breed generations and generations. There are at least 12 websites where people exchange these pets. And in fact, some lady in Australia returned one of the pets that was getting sick to the author. She wanted him to fix it, and he fixed it. He got it healthy again. Took him a whole day, and his response to that was, well, I don't know who was the more foolish, her or I. This was actually the most popular piece of software that was demoed at the Autonomous Agents Conference just recently. And they learn to speak. And if you don't speak them English, they'll invent their own language. So this is the first artificial life demo. That's the first commercial artificial life product. You can go in, you can actually edit the genetic structure of the individuals, you can monitor their health and so forth, but we don't have time to do that. So. Okay, so goodbye to the Norn there. Okay, I think we can finish up at 1:30 if that's okay. If you want to come up afterwards, I have the box at least you can look at for this creatures game. It's produced in Britain. There's a similar one out of Japan called BioBattler, in which you evolve creatures, you play with their DNA. You can have a look at that. Neither of them are available in the US. Why? I don't know. Okay, can we have the slide projector, please?
You just started.
Okay. Now, where is it? Okay, people who do a lot of simulations are often accused of never having been in the real world, and So I just want to say that I've been, 15 years I was doing archaeology and building museums in British Columbia. It was very interesting, but I found that there was basically no theory to what was being done in terms of the anthropology of that area. So one of the things I decided to do was then to come back and look for a way to build anthropological theory. This is a village, a totem pole village I used to work at. We did a lot of ethnohistoric work. We looked for old ship's logs. This is an entry, a drawing out of a ship's log from the early 1800s or late 1700s of one of the totem pole houses in the village of Custa on the Queen Charlotte Islands in British Columbia. This is almost at Alaska. We had to fly in everywhere in these float planes. It was at times risky. The doors would fall off. We got all sorts of horror stories I could tell you. A view from the bottom of about a 12-foot pit that was 2 meters by 2 meters. Lots of interesting work. There's our crew. Defying gravity. Yeah, see, look, you're in the forest. All these trees are standing upright. Whoops. I guess they all fell over. Okay. Anyway, that's the explanation. Little emergent property. A lot of the coastline was like this. We did an awful lot of archaeological reconnaissance. We were fortunate enough to be able to hire a helicopter to get into one site. The pilot really did not want to land on these rocks. But, okay, yes, that's the next slide. We were looking for a cave with pictographs, paintings. This is, as far as I know, the only example of pictographic paintings from the high down from the Charlotte Islands. If you're familiar with the culture, these are called coppers, or these are drawings of coppers, which were a form of status, something like money. This is a view into the cave, another piece of natural architecture from the helicopter. From the cave looking out, you can see somewhat the characteristics of the terrain. And some of our crew, a Hyde Indian fellow who's my adopted brother, and actually a jeweler. And a number of pictographs from very ugly looking creatures to, I don't know, cute sort of happy faced creatures with feathers on their heads. And a whole illustration of a canoe peopled with warriors, I guess. I don't know why they're standing up. It's a good way to make your canoe fall over. Again, just to kick into the idea of trying to populate, this is an architectural, well, it's a photograph of the ruins of a pre-Columbian city in Peru. If you had a map of that, threw a bunch of agents in there and were clever enough to know what to put in their heads. you might be able to figure out some of the things that could have gone on in this particular city. You've probably seen the Royal Tombs of Sipan exhibit at UCLA. Basically some ancient burial pyramids, reconstruction of them, and archaeology is pretty neat. And at times you actually find artifacts that are models of buildings. Okay, this is a chunk out of the thinking machine, the CM2 that I showed you as the initial slide from the computer. I don't know if any of you are interested in the commonalities or disjunctions between the kind of architecture you do and computer circuit architecture. It seems to me it's not just a metaphor, there are some interesting commonalities going on. I don't know. This was supposed to be a personal account, so here's some music that I really like. Anybody know Einstürzende Neubauten? Translation is new buildings falling down. Okay. This is their album, Strategies Against Architecture, and I really like their music. They play music on springs, pieces of iron, shopping carts, and so forth. It really appeals to my sense of whimsy and, I guess, anthropological background. This is the Japanese version of BioBattler. You'll notice, get God's hand, you're God in this universe. I guess metaphor or whatever. This is some detail of the various battles that you can put these creatures into. Visual metaphor, DNA. I don't know who she's a fight promoter. You breed your little creatures and you actually fight them against one another. This is the creatures demo, which you just saw. And that's one of the norms that has just hatched from this egg, which is in an incubator. You actually put the egg in there, open and close the doors, the elevators work, everything is pretty neat. I'm going to just run over this stuff really quickly. You can regard them all as pretty pictures because I don't have time to get into them, but they're all, these are pictures produced by L Systems, which is a way of reiterating ad infinitum certain motifs on others. So it's related to artificial life work. This has a pattern that is reminiscent to me of some of the architecture I've seen archaeologically. A construction in 3 dimensions produced this way, and I mentioned the notion of building artificial architecture. The researcher who did this was actually trying to design a computer software program with which he could, well, his idea was to take a swarm of 100 wasps as his agents with whatever rules they had in their heads, and they had to be real simple, and see what kind of a nest structure they would build with those rules. So this is one of the nest structures that he built. And if you're a biologist and know something about wasp nests, the intricacies of the connections and such here actually do mimic what you see in life. So this is non-human architecture, evolving architecture, insect architecture. You've probably all seen these kinds of structures. Again, they're produced by local rules, cellular automata type rules. Same with these patterns on shelves. There you're actually growing plants into the shape of the building, which is sort of a conceptually interesting that you're growing it into a house shape. Okay, the next few slides are an introduction to this video, which is coming up in just about 1 minute. It's the best example that I have seen yet, the most understandable example of using artificial life techniques, that is evolutionary techniques, to actually evolve a creature. Now the fellow who did this, his name is Karl Sims. Does anyone know his work? Okay, 1 or 2 people. He's a genius programmer. I wish I had his skills, but I don't. He used to work for thinking machines. He would do these wonderful graphics for them, just blow people away. He hasn't sat down to solve any serious biological problems yet. If we could turn his attention to doing that, it would be great for us at the Academy, but I'm sure he makes a lot more money and gets a lot more satisfaction just playing with this stuff. But here's how his system works. Basically what he has done is to evolve creatures, and here are shapes of creatures. They consist of blocks put together in different patterns. He's defined genotypes by these diagrams for the creatures, and these are the phenotypes, the shapes that these diagrams will translate into. So what he has done is in the computer to generate a population, let's say of 100 random diagrams, create 100 random creatures, put them in an artificial world with an artificial physics. Give them random, there's basically a computer at each junction, okay, or a brain at each junction that tells it how to move. Create those at random. Throw them in the computer and let them wiggle around. And the ones that move the farthest in 10 artificial seconds, he will take those and use them as the parents of the next generation of individuals. So he's actually evolving all sorts of creatures here with the fitness function. The fitness is determined by how far they move. So he's breeding critters to locomote. So this is an example of the morphologies and how they're represented inside the computer. Which button? Wrong button. Skip this one. Let's skip that one too. Here's something of an example of how the brains in these creatures work. There can be any number of sensors to pick up information about the world, connected to any number of functions or neurons in a neural net, connected to any number of effectors or motor actuators. So all this is subject to evolution as well. So not only the shape of the critter, but its whole cognitive structure, its vision, its movement, and how it coordinates that is all subject to evolution. Can we have the first video, please? You may have seen this on Nova or some science shows at various times. It's a wonderful piece with no sound. One of the remarkable things is that some of these creatures actually look like living things. They move like living things. Other of these creatures are quite bizarre. Okay. And in fact, he claimed it was a really interesting process in designing these, because whatever glitches or whatever things you introduced into the physics of this world that were not accurate, the creatures would evolve to take advantage of those strangenesses. So this runs another 5 minutes, and I think we'll stop at that point. Oh, no, we just keep going with this tape till it is. It's not done yet. Now again, there's nothing purposive about the evolution. It's just the way evolution operates, and it's producing these, I guess you call them emergences. The first runs that he did of this, he would get creatures that would build themselves up real tall and fall down, because then you see it had moved. So he had to introduce some little things into the fitness evaluation to outlaw that sort of creature. Well, the military is also working on stuff like this. They want to be able to create artificial battlefields and be able to, they already have artificial tanks that run around in these spaces. They're trying to create individual soldiers. Okay, this critter has sensors, and it's evolved to follow this, this red dot. And the way the sensors work are that any surface on that creature can be a sensor for that color, as an example. It's a really neat one. It's sort of a half helicopter thing that evolved. You'll see in a moment. So he wasn't happy with that. What he did was to evolve creatures to try to control a hockey puck. Okay, and he took long lineages of these, so he evolved something that could really control the puck, and then he took the best of all these evolutions, the best of different species, and put them together in a hockey face-off here. Now, they get points for how much they surround that object, how far away the opponent is from the object, where their center of mass is, and so forth. So these are actual tournament competitions. And you can begin to see, just from the behaviors, how their brains, whatever they are, might be functioning on somebody. Now the way their sensors work is the puck there emits one color, the opponent emits another color, and they can sense for either of those. Here was another case of critters just falling on top of the thing and winning because of that. Well, that's kind of interesting because the opponent apparently knows where everything is at the beginning, but doesn't seem to know that anything's moved. So somebody asked what artificial life is. I think Karl Sims, to a lot of people's minds, demonstrates it. This is, sort of embodies all of the motion. Another emergent behavior, go after the opponent. Forget the fuck off together. It would be nice to know what these guys are thinking, and with this technique, at least in theory, you can go back in and figure out exactly what they were thinking at any moment. Can you run that last tape? We'll end on some music and some pretty pictures from Karl Sims. It's a 2-minute video. If you have time to stay, please do. But we'll stop as soon as that other video is done. Karl Sims has done a lot of animations, remote thinking machines. This is one of them. He's also done work with the Getty to animate some of Leonardo da Vinci's sketches. Da Vinci did a sketch of the deluge. Maybe you remember that. He's actually gone in and using A-life techniques, animated that. How many of you have seen this? I should not call this animation, I should call it simulation. Okay, well, thank you all for inviting me here, and look forward to visiting you.
Nicholas is going to go to the cafe, and we'll have lunch. On any of you who are free and would like to join us, please do so. And also, if you're in the studio, if you'd like Nicholas to come by and talk to the rest of the people in the studio, tell me now before you leave, and we'll write it down.